This video is about the fundamental theorem of calculus, part 2, or abbreviated as FTC2. Now, to be clear, this fundamental theorem is broken into parts in the way that I've been laying out in these videos, but that's not the only way to explain or lay it out. There could be various authors or professors or instructors who may organize it and present it slightly differently. Ultimately, though, I like this two-part setup. I think it works well. So this is now assuming that we've already discussed part 1, which is a previous video. In part 2, we're going to use part 1, which is why it's important to use this order, at least the way I'm explaining it. And furthermore, these videos are not meant to be official formal proofs of the theorem. Those are typically in a textbook, and you could read it there. But this is more just an intuitive demonstration or to make the theorem believable and useful. We're going to start our notes with a diagram of a function, and this is actually very similar to how we laid out the part 1 video, where we have a t-axis, and this curve is an f of t function. So we'll just say that it's a curve going through quadrant 1 with a kind of a peak and a valley in it, though that's even irrelevant and just general to make the point of what's going on here. And of course, this picture happens to have that curve above the x-axis. Again, that's just the case with this picture. It doesn't mean that's always true. Now, on the t-axis, the horizontal axis, I'm going to put a few labels. And so let's just mark out 3 places here. And I'm going to label them from left to right as C, A, and B. Now you may say, well, that seems odd. Usually we say A, B, C, right? Well, I'm just kind of picking a convenient labeling scheme here to make the point clear, okay? But those letters ultimately could be anything. I'm just picking them in that way for now. Furthermore, at each of those letters, I'm going to draw some dashed vertical lines that go up to our function, kind of showing like where f of C would be, f of A, and then f of B. Of course, that would be where those function values hit directly above those letters. Using the fundamental theorem part 1 that we discussed in a previous video, let's define capital F of B as the definite integral from C to B, the way we have them labeled here, of f of t dt. Now, you'll recall when we discussed the FTC part 1 that this function, in that video we defined it as well, and it was kind of like the area so far function. In other words, this could represent, if we assume that we're using area under a curve here, which remember is only really true if this f function is positive, but it is in this picture, so we're just going with that for the explanation here. This would be like the area under the curve from C to B. So if we use maybe an orange color to mark out or shade in where that area would be, it'd be everything from C to B underneath this curve. Secondly, let's define capital F of A to be the definite integral from C to A of this f of t dt function. So similarly, this now could be seen as the area underneath the curve from C to A. So I'll shade that in a blue color. If that's the case, and that's the way we're defining those, then we could say that the definite integral from A to B of f of t would be equal to capital F of B minus capital F of A. Okay, so let me shade this in a red color. This would be, you could say, the area underneath the curve from A to B. And so if I shade that in a red color, that could be seen as this capital F of B, which is the area from C to B, take away, so in other words, the orange area, take away the blue area, is what this red area is, where, significantly, as the part 1 of the theorem said, capital F prime of x equals f of x. So in that previous part 1 video, we were using different letters like G and F, but in this case, we're using the capital F as the antiderivative of lowercase f. And remember that part 1 basically guaranteed that any continuous function has an antiderivative. So if f is a continuous function, as we're assuming it is in this case, then we could assume that it has an antiderivative that is capital F, and therefore capital F prime of x would be this lowercase f of x function. Now, it may not seem at the moment, but this is actually big news. Because what this is saying is that we can use antiderivatives to evaluate definite integrals, or even indefinite integrals, as we'll eventually see. But for now, I'm just using this in the context of definite integrals. So antiderivatives are things we've already discussed. That was doing derivatives backwards. And we also have discussed how to handle definite integrals, but only with a limit definition. And it was kind of clunky and cumbersome to do the limit definition of the definite integral, which we did recently. But now we're finally seeing here the shortcut to that limit process, and that is we can simply use antiderivatives. Now there's some important notation that can go with this, and so let's assume, as we've kind of been doing here, that capital F prime of x is equal to lowercase f of x, and so that would be assuming that capital F is the antiderivative of lowercase f. Okay, in that case, with that notation, then we could say that the definite integral from a to b of lowercase f of x dx equals, so remember, what this theorem is basically saying is that we're going to use capital F of b minus capital F of a. Well, you can write that out as we'll be doing, but one shorthand notation you may see is that it'll be written as capital F of x from a to b, and there's this notation used where you can write out capital F and then you just put a big vertical bar, or sometimes it's a vertical bar with some little feet on it, top and bottom, and then you have the bounds written on the top and bottom of it. So it might have like a at the bottom, b at the top. That actually means capital F of b minus capital F of a. So this is the theorem as we saw above, and sometimes you'll see notation written with this like vertical bar holding the bounds. It really means the same thing, and we'll see this worked out with some examples here next. Let's try some examples where we want to evaluate each integral. These are definite integrals. The first example is the integral from 0 to 1 of the function 1 minus 8v cubed plus 16v to the 7th dv. Now, if we understand our fundamental theorem above, this part 2 of it, we know that we can actually shortcut this process of finding a definite integral simply by using the antiderivative of this function evaluated at the bounds in the respective way. So we're going to write out the antiderivative of this function as we know of those already using the shortcut rules. So instead of 1, remember our independent variable here is v, so instead of 1 the antiderivative would just be a single v. Instead of minus 8v cubed, remember we'll say minus 8v, and then remember we increase the power by 1 and then divide by the new power. That's the shortcut power rule for antiderivatives. That's all we're using here. And then we'll move on and say plus, we'll say 16, same rule here, so v to the 8th over 8. And now we're hopefully really in the habit of putting a plus c at the end of our antiderivatives. And we've discussed the reason for that general arbitrary constant, but we're actually not going to need the plus c in the context of definite integrals, and we know it's definite because it's given with the bounds of integration here. Okay, the reason is that constant will always disappear or cancel out in this next step. Now remember, I haven't fully written this yet. We've simply taken the antiderivative of our function. But remember, with the notation you may see, often you'll see the antiderivative written with the lower bound and upper bound written kind of at the high and low places of this vertical bar. Okay, so that means we actually now want to evaluate it first at f of b, this is b at the top, and then f of a, which is a at the bottom, or I should say capital F of those, respectively. So I'm going to plug in 1 first, and that would mean 1 minus 8 times 1 to the 4th over 4 plus 16 times 1 to the 8th over 8. That's, if I could note, that's capital F of 1, or in other words, capital F of b. But now I have to subtract capital F of a, which is capital F of 0 in this case. And so in that way, I'll write out 0 minus 8 times 0 over 4, that's 0 to the 4th there, plus 16 times 0 to the 8th over 8. Alright, so obviously that one's going to get simple much quicker, but that second piece, that's F of 0. So this is F of 1 minus F of 0, kind of like the F of B minus F of A. All we do now is simplify these by arithmetic, and this would be 1 minus 8 over 4, which is really 2, plus 16 over 8, which is really 2, and then minus a whole bunch of zeros, which should ultimately give us just 1 if we simplify all the arithmetic with that. Now, regarding the constant that I just mentioned, the constant of integration, it would cancel out every time because I could say I would have had a plus c in the f of 1, but then I would also have a plus c in the f of 0, but this negative would be distributed to it, which means I would always get, a plus c and then a minus c, and those would cancel out every time, so we don't even have to consider the constant. We'll just say 1 is our answer for this definite integral. Let's try some more examples in the same way. Example 2 is the definite integral from 1 to 8 of our function is x to the negative 2/3 power dx. Well, if we're using the fundamental theorem of calculus to evaluate this, we know we can do so with the antiderivative of this function evaluated at the bounds in the right order. So we'll go ahead and use the power rule for the antiderivative of x to the negative 2/3, which would include adding 1 to the power. So notice, if it's negative 2/3 to begin with, then really 1 would be 3/3. So if I add 3/3 to negative 2/3, that would give me a 1/3 power result for my new power, but then I divide by the new power of 1/3. Now that's the antiderivative of our function, but since this is a definite integral, as we've just discussed, we really want to evaluate that at the bounds from 1 to 8, where 1 is like the A and then 8 is the B. And so that would mean I first plug in 8, and by the way, we can simplify a little bit of the algebra here. If I took this 1/3 down below and kind of flipped it up and over, it really would be a 3 out in front of the x in our function. That's just a way to simplify it. So really I have 3 times 8 to the 1/3, that's f of b, using 8 for b, okay, minus f of a would be 3 times 1 to the 1/3, and so ultimately 8 to the 1/3 is 2, which means we have 3 times 2, which is 6, minus, and then this is really just 3 times 1, which is 3, so 6 minus 3 would be 3. So that's our result. Notice it used the fundamental theorem, which is simply using an antiderivative and evaluating it in this f of b minus f of a format, as we discussed above in our theorem, as a way to know this definite integral without even taking a limit. Let's try a next example. This one is given as the definite integral from negative 5 to positive 5 of e dx. So notice e, that's the number e, which is designated as a special number here. And those bounds are given as negative 5 to 5, but we just need the antiderivative first. Now, if the independent variable is given as x, the variable of integration here, then e is really a constant, and the antiderivative of a constant would be to make it e times x, or e times x to the first, you could say. That's just using our regular antiderivative form or formula for a constant function. But now we want this evaluated at the bounds, so really from negative 5 to positive 5. Okay, and so we can plug in the upper bound first, that's the f of b. That would mean e times 5 minus, and then the lower bound would mean e times negative 5. And so we could mean this is really 5e plus 5e, which is really just 10e as our result. Our next example is the definite integral from 0 to 4 of the function which has really two factors. The first factor is 4 minus t in parentheses, and the second factor is the square root of t. So it's 4 minus t times the square root of t dt. Now, notice that this function is, if you think to antiderivatives, it's going to require us to use maybe one little simplifying step beforehand. Using the rules we already know for antiderivatives, we would prefer to see this written as separate power functions instead of this product of 4 minus t times the power function, really t to the 1/2. So what we would have done in the context of taking an antiderivative would be to distribute this square root of t as a t to the 1/2. So let's write this out a little bit more. We have the integral from 0 to 4 of 4 minus t times t to the 1/2 dt, and we're going to distribute that t to the 1/2 inside, ultimately to end up with the integral from 0 to 4 of 4t to the 1/2 minus, and then when I multiply the t to the 1/2 times the t, remember I'll be adding those powers. That'll give me t to the 3/2 and then dt. Now we'll go ahead and use our fundamental theorem by taking the antiderivative of each term, which would give us 4t to the, remember, increase that power by 1, that would give us t to the 3/2, but then we'd be dividing by that new power of 3/2. Okay, a little fraction work to clean up there, but we'll keep moving for now. Okay, minus to the second term, it was t to the 3/2. We're going to be adding 1, which is really 2/2 to that, which would give us t to the 5/2, but then we divide by the 5/2, the new power as well there. And ultimately we want to evaluate this at the bounds from 0 to 4. Now let's do a little bit of the fraction simplification here. If I kind of judo flip these fractions to simplify them and put them in front, I really would have in this first term 4 times 2/3. If I flip that fraction over and use the reciprocal, that would become 8/3 times t to the 3/2 minus, similarly I'd have 2/5 for the second term, t to the 5/2, and this is all still needing to be evaluated from 0 to 4. Remember, this means f of b minus f of a, where that means f of 4 minus f of 0, using the notation of our theorem written above. So I want to plug in 4 first, the upper bound. That would give me 8/3 times 4 to the 3/2 minus 2/5 times 4 to the 5/2. There's f of 4, f of b, you could say. Okay, now I need to subtract f of a. Well, thankfully that's simple. That's just saying 0 minus 0, because when you plug in 0 with these t's, they all turn to 0, which makes it a lot better. Now, this kind of problem would require some arithmetic simplification, and depending on your instructor's policy, you may have different ways to handle that. My policy is, at this point, if you've shown all of this work, you can use a calculator for this kind of arithmetic, and this would give us a 1/28/15 as a simplified result for this definite integral. Let's try another example. This one is the definite integral from pi over 4 to pi over 3, and that is of cosecant squared of theta d theta. Now, in this case, we want to use the fundamental theorem to evaluate this definite integral, which will involve using the antiderivative of cosecant squared of theta. Hopefully those antiderivatives are sticking in your memory by now as we've been practicing them. That is actually one of our antiderivative formulas that we know for our common functions, and this should turn into negative cotangent of theta. So in other words, the derivative of cotangent is negative cosecant squared, but we're starting with a positive cosecant squared going backwards, which means we have to throw the negative in with this antiderivative. So there's the antiderivative. We want that evaluated at the bound. So from pi over 4 to pi over 3, and we'll go ahead and plug those in respectively. This would become negative cotangent of pi over 3 minus negative cotangent of pi over 4. Be careful with all the negatives in these kinds of examples. It's easy to get them mixed up, especially when you have this double negative going on in the middle there. If we ultimately evaluate this according to trigonometry as we've understood it, this is really like a negative 1 over root 3 minus a negative 1. And if we simplify that just a little bit, we could maybe rewrite that as 1 minus 1 over root 3. Yes, you could rationalize that, just go with whatever standard the textbook is using or your instructor is using. I'd be fine with leaving it right as it is here. Let's try a sixth example. For this one, we have the definite integral from 1 to 18 of our function, which is the square root of 3 over z, and then we have dz. In order to evaluate this with the fundamental theorem and use the antiderivative in the process, I think it's actually more convenient to rewrite this as the integral from 1 to 18 of the square root of 3 times z to the negative 1/2. If you just think through the algebra of that, that's equivalent to this original function, and of course this is all still dz, but this gives us a power function to use, which we can do antiderivatives of very easily. Furthermore, let's recall that when you have a constant in front of your function in the integrand, we wrote it as c in some of our properties earlier on, that constant can be thrown out in front, which means I could rewrite this as the square root of 3 times the integral from 1 to 18 of z to the negative 1/2 dz, and then I just do the antiderivative of this power rule, but I'm going to keep this square root of 3 with it, so this will become now z to the positive 1/2 over 1/2. That's adding 1 to this power and then dividing by that new power of 1/2. And then of course this needs to be evaluated at the bounds, so from 1 to 18. Now if we clean this up with a step or two, again we'll kind of judo flip this fraction in the denominator up above to make this 2 root 3 times z to the 1/2 evaluated from 1 to 18. And so f of b, in other words f of 18, would be plugging that in. Now with a constant in front of our function as it's ended up here, you actually could do it two different ways. You could bring the constant, in this case 2 root 3, with the function pieces as you evaluate the capital F of b minus capital F of a, or you could kind of consider that constant to just be out in front of this antiderivative piece here we're going to use. It should result the same way either way. I like to keep, if I have a constant out front and it makes it simpler, I like to just keep it out front. I'll put some parentheses around this fundamental theorem piece we're going to do, but I'm going to leave this 2 root 3 just out front. So that means when I actually write it out, I'm going to put the 2 root 3 and then in parentheses, that's where I'll do the f of b minus f of a thing, where again b is 18, so that would be the square root of 18, that's plugging it in for z to the 1/2. There's f of b minus, and then it'd be square root of 1 for f of a. And then this could result, as I could distribute this 2 root 3, to be 2 root 3 times, actually let's simplify once quickly before. The square root of 18 is really 3 root 2. If you simplify that, right, 18 is really 9 times 2. You can split that up, square root of 9 is 3. And so that's really the case there, minus the square root of 1 after that. If I now distribute this 2 root 3, I could get, if I clean this up, 6 root 6 minus the square root of 1. Or perhaps you could even leave it at the previous step without distributing the 2 root 3. Either way, that should be our result for that one. Let's try another example. This one is the definite integral from 1/2 to 1 over the square root of 2 of the function 4 over the square root of 1 minus x squared dx. Now, this one perhaps looks a little complex. Let's see if we can pick it apart and recognize some key pieces to it. First of all, this constant in the numerator could be understood as really it's like a 4 times 1 over this denominator, which means I could pull that constant out in front of the integral, as we know from our property, and rewrite this as 4 times the definite integral from 1/2 to 1 over the square root of 2 of 1 over the square root of 1 minus x squared dx. You may recognize this inner integrand function now as really a common derivative, one of our common derivatives. So let's rewrite this as 4 times, and maybe you guessed it, it's really the arc sine, or you could say the sine inverse, same thing, of x. That would be the antiderivative of that inner function. And we want this evaluated from 1/2 to 1 over the square root of 2. But that's really 4 times, if I just keep the constant of 4 out in front and then do the fundamental theorem stuff just with the arc sign or the sine inverse, then we really have, I'll use the other notation here just to be clear that it doesn't matter which, we really have the sine inverse of 1 over root 2, which, depending on how you had this in trig, that's the same thing as root 2 over 2 if it's rationalized. That might be more familiar. So there's f of b minus f of a, would be plugging that in. That's the, for the lower bound, that's the sine inverse of 1/2. Okay, so that's written with the sine inverse notation instead of the arc sign. It's really the same thing. Pick your poison there. And then this could be simplified to be 4 times, it's really pi over 4 minus pi over 6, if you review some of the trig involved with that, which is ultimately pi minus 2 pi over 3, or 2/3 pi, which is ultimately 1/3 pi, or you could just say pi over 3 for that result. And let's try another example where we want the definite integral from -2 to 2 of f of x dx, where f of x is defined as a piecewise function. So we have f of x equals 2, just the constant 2, if x is between -2 and 0, inclusively, or f of x is equal to 4 minus x squared if x is between 0 and 2, inclusive at 2, exclusive at 0. Now notice that the way this function is defined, and even this integral, this definite integral, we're trying to integrate from -2 to +2, but the way the function is defined is different depending on whether you are to the left of 0 or to the right of 0. So we're actually going to have to split this definite integral up into 2 other definite integrals where the bounds are different. So we can have one from a -2 to 0, and then one from 0 to 2, and we split it there again because of the boundaries given in this piecewise definition. So from -2 to 0, my function is defined simply as 2. That was the first piece, and then we'll say dx. So 2 dx for the first integral. In the second piece, from 0 to 2, our function was defined as 4 minus x squared, so we'll put it that way, dx. And then we just do, as you can imagine, we've split this definite integral really into 2 different definite integrals, but they each get treated the same way with this fundamental theorem shortcut. So we're going to rewrite the first piece, which had the function 2 as now 2x, that's the antiderivative of 2, but we want that evaluated from -2 to 0. And then we'll go on to the second piece. The antiderivative of 4 minus x squared would end up being 4x minus x cubed over 3, and that's evaluated from 0 to 2. If we apply our fundamental theorem to this, we'll evaluate at these bounds. In the first piece, we have plugging in 0, so that would be 0 minus, and then plugging in the lower bound would give us a -4. So again, be careful with the negatives. This would be 0 minus -4 for the first part of this, the first definite integral that we split off. Moving on to the next one, if we plug in its upper bound first, so plugging in 2, that would give us 8 minus 8/3. So there's like f of 2 minus f of 0. Plugging in 0 would just give us 0. Now, let's be clear here. You may think, according to all these parentheses, that we've messed something up because shouldn't there be a minus between the pieces? Well, remember, this plus sign we're seeing here corresponds with the plus sign that was between these definite integrals we used to capture this function in 2 different pieces. So the minus that comes with the fundamental theorem is actually the minus you see within these parentheses. So the 0 minus -4, it's that minus, and then secondly it's the 8 minus 8/3 minus 0, it's that minus. Those are the minuses that go or come from the f of b minus f of a in the theorem. And again, ultimately, if you show this much work, you can use a calculator to help with some of the arithmetic. I think this one should turn out to be 28/3. And we want exact answers, no rounded decimals or anything. So nice reduced fractions. They could be improper, but let's leave exact solutions for these.